something 7 billion years old is racing through our solar system right now at 209,000 kilometers per hour. It's older than Earth. It's older than our Sunday. And scientists just discovered something about it that's making them question everything they thought they knew about the universe. This ancient visitor carries memories from when the cosmos was young, when stars were just beginning to form in ways we've never seen before. Tonight, we're going to follow this cosmic wanderer as it reveals secrets that have been hidden in the darkness of space for longer than our entire solar system has existed. You're about to hear a story that spans billions of years, and by the end, you'll understand why this might be our only chance to touch something truly ancient. The object has a name. 3 I divided by Atlas. The third interstellar visitor we've ever detected, but unlike anything we've encountered before. When astronomers first spotted it on July 1st, 2025, using the Atlas Survey telescope in the mountains of Chile, they thought they were looking at just another comet. They were wrong. What they found was something that shouldn't exist according to our models of how comets behave. Something with chemistry so unusual that it's forcing scientists to rewrite textbooks. Something that might be carrying the building blocks of life from an era when the universe itself was fundamentally different. But here's the challenge we face. This visitor, this messenger from the deep past, is moving fast. Really fast. And our window to study it, to understand what it's trying to tell us about the early universe, is closing. Every day that passes, 3 I divided by Atlas moves further away, taking its secrets with it. But wait until you hear what scientists discovered when they looked deeper into its chemistry. The readings they got were so bizarre that some researchers thought their instruments were broken. The age mystery. Let me paint you a picture of just how old this thing really is. Imagine if you could compress the entire history of the universe into a single year. If the Big Bang happened on January 1st, then 3 I divided by Atlas formed sometime around March. Our solar system? That didn't come into existence until September. Earth formed in late September. The first life on our planet appeared in October. Dinosaurs lived and died in just the last week of December. And all of human history would fit into the last few seconds before midnight on New Year's Eve. 3 I divided by Atlas has been wandering through space since March of that cosmic year. It's a relic from cosmic noon, the peak era of star formation when the universe was young and violent and creative in ways we can barely imagine. But let's start with how we found it, because that story alone reveals something extraordinary about this visitor. The discovery wasn't actually made on July 1st. That's just when astronomers officially recognized what they were looking at. The real story begins weeks earlier, buried in archives of data that no human had looked at yet. You see, our modern telescopes capture so much information every night that we rely on computer algorithms to spot interesting objects. But sometimes, something special hides in that data, waiting. The Transiting Exoplanet Survey satellite TESS had actually photographed 3 I divided by Atlas on May 7th, 2025, when it was still 6.4 times further from the Sun than Earth is. At that distance, most comets are just cold, dark rocks. But 3 I divided by Atlas was already active, already glowing, already defying expectations. The Zwicky Transient Facility had captured it too on June 14th. 3 different observatories had seen this object, recorded its light, stored the data, and moved on. It was only when astronomers went back through the archives after the official discovery that they realized they'd been watching something unprecedented for weeks. This kind of archaeological astronomy reveals something profound about 3 I divided by Atlas. Most comets only become active when they get close enough to the Sun for water ice to start sublimating, usually inside the orbit of Mars. But 3I divided by Atlas was active out beyond Jupiter's orbit. Something else was powering it. That something was carbon dioxide. But what happened when the most powerful space telescope ever built turned its attention to this ancient wanderer would shock the scientific community and force them to question everything they thought they knew about comet chemistry? The chemical impossibility. When the James Webb Space Telescope turned its golden eye toward 3I divided by Atlas, what it saw was unlike any comet in our solar system. The Webb telescope can analyze the chemical composition of objects by studying how different molecules absorb and emit light. It's like taking a chemical fingerprint of something millions of kilometers away. The fingerprint of 3I divided by Atlas was bizarre. Most comets have a carbon dioxide to water ratio of around 1:1. Some comets from the outer solar system might have ratios as high as 2:1. 3I divided by Atlas has a ratio of 7.6 1:1. That's 4.5 standard deviations above what we've ever measured. In statistical terms, that's like finding a person who's 8 feet tall. Something so rare it happens maybe once in a million cases. But the strangeness doesn't stop there. When astronomers analyzed the other chemicals in 3I divided by Atlas, they found something even more puzzling. High concentrations of nickel, but almost no iron. In the cosmos, nickel and iron usually go together. They form in the same stellar processes, get mixed together in the same cosmic events, travel together through space. Finding one without the other is like finding salt without sodium or water without hydrogen. It just doesn't happen. Unless you're dealing with something that formed under conditions we've never seen before. The spectrum analysis also revealed the presence of carbonyl sulfide, a molecule that's relatively rare in space. And when astronomers measured the isotope ratios, the different versions of the same elements, they found signatures that suggested this comet had experienced things no solar system object ever has. Dr. Sarah Chen, one of the lead researchers studying 3I divided by Atlas, described it this way. It's like reading a book written in a language we recognize, but with grammar rules that don't exist in any language we know. But the chemical oddities were just the beginning. When astronomers tried to figure out how big 3I divided by Atlas actually is, they ran into another puzzle. The Hubble Space Telescope can usually measure the size of comet nuclei pretty accurately by looking at the solid core beneath all the dust and gas. But when Hubble looked at 3I divided by Atlas, it couldn't find the nucleus. Not because it wasn't there, but because it was completely hidden beneath an enormous cloud of dust and gas. But what they discovered about this dust cloud would lead to one of the most shocking revelations about 3I divided by Atlas yet. The measurements were so extreme that multiple research teams had to verify their equipment wasn't malfunctioning. The size paradox. The coma, that's what astronomers call the cloud around a comet, extended for over 3 arc minutes across the sky. To put that in perspective, that's about 1/10 the apparent size of the full moon. For something so far away to appear that large means the coma is absolutely enormous, hundreds of thousands of kilometers across. Here's what's strange about that. The total brightness of 3I divided by Atlas suggests the solid nucleus, the actual rocky icy core, is somewhere between 320 meters and 5.6 kilometers across. But over 99% of the light we see is coming from the dust cloud, not the nucleus itself. It's like trying to see a person standing behind a massive dust storm. You know they're there, but they're completely hidden. This presents a paradox. Either 3I divided by Atlas has an incredibly small but incredibly active nucleus, more active than any comet we've ever seen. Or it has a larger nucleus that's somehow hidden beneath this dust shroud in a way we don't understand. The activity levels are important because they tell us about the internal composition and structure of the comet. Most comets become less active as they age and lose their volatile materials. But 3I divided by Atlas, despite being billions of years old, is more active than most young comets in our own solar system. Then there's the polarization mystery. When light bounces off an object, it can become polarized, meaning the light waves orient themselves in particular directions. Different materials polarize light in different ways. So, by measuring polarization, astronomers can learn about what an object is made of and how its surface is structured. The polarization measurements of 3I divided by Atlas were unlike anything ever recorded. Using telescopes at the Very Large Telescope Observatory in Chile, the Nordic Optical Telescope in Spain, and the Rozhen Observatory in Bulgaria, astronomers measured a negative polarization of 2.7% at a phase angle of 7 degrees. Those numbers might not mean much to you, but to astronomers studying comets, they were shocking. No comet, no asteroid, no solar system object has ever shown that combination of polarization and phase angle. It suggests the surface of 3I divided by Atlas is composed of unusually large particles mixed with both icy and dark materials, possibly arranged in a highly porous structure unlike anything in our solar system. Dr. Maria Rodriguez, who led the polarization studies, said it was like discovering a new color. The measurements were so far outside the known range that the team spent weeks double-checking their equipment and calculations before publishing the results. But the most intriguing discovery was yet to come. When astronomers traced the path of 3I divided by Atlas backward through time, what they found would completely change our understanding of where this ancient visitor came from. The galactic journey. Most interstellar objects, including the previous visitors 1I divided by Oumuamua and 2I divided by Borisov, originated from the thin disk of our galaxy, the region where most stars like our sun are born and live. But 3I divided by Atlas appears to have come from the thick disk, a much older region of the galaxy populated by ancient stars that formed when the universe was young. Astronomers figured this out by running the orbit of 3I divided by Atlas backward through time, using computer simulations to trace its path through the gravitational field of our galaxy. These Monte Carlo orbital integrations, as they're called, suggest that 3I divided by Atlas has been wandering through space for between 7.8 and 10.3 billion years, with a median estimate of 9.6 billion years. To understand what this means, you have to understand the structure of our galaxy. The Milky Way isn't just a flat disk of stars. It's more like a fried egg, with a thin disk where most of the young metal-rich stars live, surrounded by a thicker disk of older, metal-poor stars, all surrounding a central bulge and embedded in a spherical halo of the oldest stars. The thick disk stars formed during the early epochs of galactic evolution, when the universe had different chemistry, different star formation rates, different everything. These stars were born from gas clouds that hadn't been enriched by as many generations of stellar death and rebirth. They represent a different era of cosmic history, and 3I divided by Atlas appears to be a refugee from that era. The orbital analysis suggests it was ejected from a planetary system around a thick disk star during the early phases of that system's formation. Back then, the process of planet formation was messier, more violent. Large objects regularly got flung out of their birth systems to wander the galaxy as interstellar nomads. For nearly 10 billion years, 3I divided by Atlas has been traveling through the Milky Way, occasionally passing close to other stars, getting gravitational nudges that slowly changed its trajectory. Each stellar encounter was like a cosmic billiard ball collision, adding energy and changing direction. The hyperbolic excess velocity of 3I divided by Atlas, the speed it has relative to the average motion of stars in our region of the galaxy, is about 57 to 58 kilometers per second. That might not sound like much, but it represents billions of years of accumulated gravitational kicks from stellar encounters. Think about that for a moment. This object has been wandering through space since before our solar system existed. It's witnessed the birth and death of countless stars. It's passed through nebulae, survived supernova shockwaves, traveled through regions of space we can only dream of exploring. It's a cosmic time capsule, carrying with it the chemical fingerprints of an era we can study no other way. But here's something that makes this story even more remarkable. When astronomers started analyzing spectroscopic data from 3I divided by Atlas, they found something that challenges our fundamental understanding of how comets behave. And what they discovered hiding in the data would open up entirely new questions about the possibility of life in the early universe. The organic mystery. In August 2025, ground-based telescopes detected cyanide gas in the coma of 3I divided by Atlas. Cyanide might sound scary, but it's actually common in comets. What was uncommon was the ratio of different carbon chain molecules. 3I divided by Atlas showed unusually low ratios of C2 to Cn, placing it among the most carbon chain depleted objects known. This depletion pattern provides insights into the chemical processing that occurred in its parent protoplanetary disk billions of years ago. Different temperature and radiation conditions in the disk would have favored different chemical reactions, creating different molecular ratios. The ratios in 3I divided by Atlas suggest it formed in conditions unlike anything we see in planetary systems forming today. The comet's spectral slope, the way its brightness changes across different wavelengths of light, is also unusual. At 16-18% per 100 nanometers in the red direction, it resembles D-type asteroids and some trans-Neptunian objects. This reddish coloration typically indicates surface materials that have been processed by cosmic ray bombardment over geological timescales. Imagine being hit by high-energy particles for billions of years. That's what the surface of 3I divided by Atlas has endured during its interstellar journey. Cosmic rays, the high-energy particles that stream through space from exploding stars and other violent cosmic events, have been slowly altering the chemistry of its surface. This radiation processing creates complex organic molecules and changes the optical properties of materials in ways we're still learning to understand. Near-infrared spectroscopy has revealed complex grain-size distributions and compositions that don't match typical solar system comets. The grain sizes suggest a surface that's been modified by processes we don't see in our local cosmic neighborhood. Some researchers speculate that the long exposure to the interstellar medium, the thin gas and dust between stars, has altered the surface composition in subtle but measurable ways. Recent reanalysis of the James Webb Space Telescope data has suggested the presence of additional molecular species in the coma that weren't initially detected. Trace amounts of hydrogen sulfide, ammonia, and possibly even more complex organic compounds are hiding in the spectroscopic signatures, requiring sophisticated modeling to separate their contributions from the overwhelming carbon dioxide signal. These trace components might provide even more detailed information about the formation environment of 3I divided by Atlas. The relative abundances of different sulfur and nitrogen-bearing compounds reflect the temperature, pressure, and chemical conditions in the protoplanetary disk where the comet formed. Each molecular ratio is like a thermometer or barometer reading from 10 billion years ago. Dr. Michael Jung, who led the reanalysis effort, describes the process as archaeological chemistry. Just as archaeologists piece together ancient cultures from pottery fragments and tool marks, astronomers are reconstructing the conditions in an ancient stellar system from molecular fragments in a comet's coma. The hydrogen sulfide detection is particularly interesting because it suggests the presence of sulfur chemistry that's rare in solar system comets. This might indicate that the parent system of 3 I divided by Atlas had a different sulfur inventory than our solar system, possibly due to different types of stellar nucleosynthesis in the thick disk stellar population. The ammonia detection provides clues about nitrogen chemistry and temperature conditions during formation. Ammonia is easily destroyed by radiation and heat, so its preservation over billions of years suggests either very cold storage conditions during the interstellar journey or efficient protection mechanisms within the comet nucleus. The possible detection of more complex organic compounds is the most tantalizing finding. While the spectroscopic signatures are still being analyzed and confirmed, preliminary results suggest the presence of molecules with 5 or more carbon atoms, possibly including amino acid precursors or other prebiotic compounds. But what astronomers discovered about the rotational behavior of 3 I divided by Atlas would prove to be one of the most perplexing mysteries of all. The measurements defied every prediction and challenged our understanding of how objects behave in space. The rotational enigma. But one of the most puzzling aspects of 3 I divided by Atlas is its rotational behavior, or rather, the lack thereof. Most comets spin, and as they spin, their brightness changes depending on their shape and how light reflects off different parts of their surface. These brightness variations can be quite dramatic. 1 I divided by Oumuamua, for example, showed brightness changes of 3.5 magnitudes, suggesting it was either highly elongated or had very different reflectivity on different sides. 3 I divided by Atlas shows almost no rotational variation at all. There's a possible 16.1 6-hour rotation period, but the brightness only changes by about 0.3 magnitudes. This stability is puzzling. It suggests either a nearly spherical nucleus, which would be unusual for a comet, or viewing geometry effects that hide the rotation, or that the activity in coma are so extensive that they mask any underlying rotational variations. The lack of clear rotational signatures makes it difficult to determine the exact shape and orientation of the nucleus. It's like trying to figure out the shape of an object inside a fog bank. The fog obscures all the details you need to make sense of what you're looking at. Recent attempts to detect rotation using more sophisticated analysis techniques have yielded tentative results. Fourier analysis of the light curve suggests possible periodic components at several different periods, including the previously mentioned 16.1 6-hour period and possibly additional periods at 8.2 hours and 32.4 hours. These multiple periodicities might indicate that 3 I divided by Atlas is in a complex rotational state with multiple axes of rotation, a condition that can arise from gravitational torques during close stellar encounters or from outgassing that creates non-uniform forces on the nucleus. The rotation mystery connects to broader questions about how long-term interstellar travel affects the physical properties of small bodies. Billions of years of cosmic ray bombardment, temperature cycling, and gravitational perturbations could significantly alter the shape, composition, and rotational state of objects like 3 I divided by Atlas. Understanding these long-term evolution processes is crucial for interpreting observations of interstellar objects and for understanding what they can tell us about their formation environments. If interstellar travel significantly modifies the properties of these objects, then we need to account for those changes when trying to reconstruct their original characteristics. This rotational mystery connects to another puzzle, the magnetic properties of 3 I divided by Atlas. But when multiple spacecraft detected something unprecedented about this ancient visitor, the scientific community was forced to confront a phenomenon they had never seen before: the magnetic anomaly. Multiple spacecraft, including the Solar and Heliospheric Observatory, the Parker Solar Probe, and the Mars Atmosphere and Volatile Evolution mission, simultaneously detected magnetic field disturbances associated with the passage of 3 I divided by Atlas. This is extraordinary because objects of this size typically don't have sufficient magnetic fields to deflect solar wind particles over large distances. The magnetic signatures suggest either an intrinsic magnetization of the nucleus, which would be unusual for a comet, or complex interactions between the coma and interplanetary magnetic field lines. Neither possibility fits well with our current understanding of how comets behave. Dr. James Thompson, a magnetospheric physicist at the European Space Agency, described the magnetic observations as opening a new chapter in our understanding of small body interactions with the solar wind. The magnetic data suggests that 3 I divided by Atlas might have internal properties we've never encountered before. Some researchers have speculated that the long interstellar journey might have allowed the object to accumulate magnetic minerals or develop unusual magnetic properties through processes we don't fully understand. Others suggest that the unique chemistry and high activity levels might create electromagnetic effects we haven't seen in other comets. The magnetic anomaly has practical implications too. It affects how the solar wind interacts with the coma, potentially influencing the development and evolution of the dust and gas cloud around the nucleus. This could explain some of the other unusual properties we've observed. The Parker Solar Probe, which was relatively close to the Sun during the passage of 3 I divided by Atlas, detected magnetic field disturbances that correlate with the comet's orbital position with remarkable precision. The magnetic signatures suggest that the interaction between 3 I divided by Atlas and the solar wind is more complex than initially thought. Rather than a simple deflection of solar wind particles, the data indicates a structured interaction region with multiple components and varying intensity. Dr. Catherine Rodriguez, a space plasma physicist analyzing the Parker Solar Probe data, describes the magnetic environment around 3 I divided by Atlas as unlike anything we've seen from a comet. The structured nature of the interaction suggests either an intrinsic magnetic field from the nucleus itself or complex electromagnetic processes within the extended coma. The magnetic field measurements are also providing new insights into the physical structure of the coma. The way magnetic field lines drape around and through the coma reveals information about the density distribution and dynamics of the dust and gas cloud that can't be obtained through optical observations alone. Some researchers are developing models that combine the magnetic field data with the spectroscopic and photometric observations to create three-dimensional maps of the coma structure. These models reveal a complex dynamic environment with multiple regions of different density, composition, and magnetic properties. But all of these discoveries pale in comparison to what researchers found when they looked more closely at the timing and trajectory of this ancient visitor. What they uncovered would challenge everything we thought we knew about cosmic coincidence. The impossible timing. Perhaps the most profound aspect of 3 I divided by Atlas isn't any single unusual property. It's what the combination of all these properties tells us about the diversity of objects in our galaxy. Until recently, we thought we understood comets pretty well. Water ice, carbon dioxide, dust, some rocky materials, all mixed together in proportions that made sense based on where and when they formed in our solar system. The first interstellar visitors challenged that understanding a bit. But 3I divided by Atlas completely shatters it. This single object is showing us that the processes of planet formation, the chemistry of protoplanetary disks, the effects of long-term cosmic ray exposure, the dynamics of galactic evolution, all of these things can combine in ways we never imagined to create objects, unlike anything in our local cosmic neighborhood. It's making us realize that our solar system, for all its diversity, represents just one small sample of the possibilities in the universe. There are trillions of star systems in our galaxy alone, each one potentially creating objects with different properties, different compositions, different histories. And sometimes, very rarely, one of those objects finds its way to us. The trajectory analysis reveals something else remarkable about 3I divided by Atlas. Its orbital plane lies nearly in the ecliptic, the same plane where Earth and the other planets orbit the Sunday. This is unusual for an interstellar object, which could approach from any direction. Additionally, it makes unusually close approaches to Venus, Mars, and Jupiter, and achieves perihelion, its closest approach to the Sun, on the side opposite from Earth. These characteristics led some researchers to speculate about whether 3I divided by Atlas might be artificial rather than natural. Harvard astronomer Avi Loeb, known for his willingness to consider unconventional possibilities, has highlighted these orbital peculiarities as potentially significant. The speculation isn't entirely without merit. If you were designing a trajectory to study our solar system, you might choose something similar to what 3I divided by Atlas is doing. The close approaches to multiple planets would provide gravitational assists and opportunities for observation. The timing of perihelion would allow extended observation while remaining hidden from Earth-based telescopes during the closest approach. But the overwhelming scientific consensus supports a natural origin. The chemical composition, while unusual, makes sense in the context of formation in an ancient protoplanetary disk. The physical properties, while extreme, fall within the range of what's theoretically possible for natural objects. And the orbital characteristics, while interesting, can be explained by the complex gravitational dynamics of objects ejected from distant stellar systems billions of years ago. Dr. Lisa Chen, who led one of the comprehensive studies of 3I divided by Atlas, put it this way: extraordinary claims require extraordinary evidence. While 3I divided by Atlas is certainly extraordinary in many ways, all of its properties can be explained by natural processes, even if some of those processes are extreme or unfamiliar to us. The speculation does highlight something important, though. 3I divided by Atlas is so unlike anything we've seen before that it challenges our preconceptions about what's possible in nature. It's a reminder that the universe is far stranger and more diverse than we often assume. And that brings us to one of the most exciting aspects of the 3I divided by Atlas story: what it means for the future of interstellar object discovery. But there's something about the timing of this discovery that goes beyond mere scientific significance. Something that suggests we might be living through one of the most extraordinary coincidences in cosmic history: the future observatory revolution. The Vera Rubin Observatory, currently under construction in Chile, is predicted to discover several interstellar objects every year once it becomes operational. This dramatic increase in detection rates will transform our understanding of the galactic population of ejected planetary building blocks. Right now, we have a sample size of 3. 1I divided by Oumuamua, 2I divided by Borisov, and 3I divided by Atlas. 3 objects don't make a statistically significant sample for understanding the diversity of interstellar visitors. But when the Rubin Observatory is fully operational, we'll be detecting dozens of these objects every year. Imagine having not 3 examples of interstellar objects, but 300. We'll be able to study their compositions, their sizes, their orbital characteristics, their activity levels. We'll start to see patterns and correlations. We'll begin to understand which types of stellar systems produce which types of ejected objects. We'll map the chemical evolution of different regions of our galaxy based on the wandering refugees we capture passing through. The Legacy Survey of Space and Time, the primary mission of the Rubin Observatory, will create the most comprehensive map of the changing sky ever attempted. It will observe the entire visible sky every few nights for 10 years, creating a time-lapse movie of the cosmos that will reveal not just interstellar visitors, but supernovae, asteroid impacts, stellar explosions, and countless other transient phenomena. In this flood of discoveries, objects like 3I divided by Atlas will go from being unique curiosities to members of a diverse population that we can study statistically. We'll learn about the typical properties of interstellar objects and what makes some of them unusual. We'll trace their origins back to different epochs of galactic history and different types of stellar environments. But there's something bittersweet about this perspective. Each interstellar visitor is unique, carrying its own individual history through the cosmos. 3I divided by Atlas has been alone in space for nearly 10 billion years. It's witnessed the evolution of our galaxy from a younger, more chaotic place to the more mature, organized structure we see today. During its journey, entire generations of stars have been born, lived their lives, and died. Planetary systems have formed and evolved. Some may have developed life, intelligence, civilization. Others may have been destroyed by stellar explosions or cosmic catastrophes. 3I divided by Atlas has seen it all, a silent witness to the grand story of cosmic evolution. And now, for a brief moment in cosmic time, this ancient wanderer is passing through our solar system. We have maybe a few years to study it before it disappears back into the depths of space, continuing its billion-year journey to destinations we can only imagine. The window for spacecraft intercept missions is closing rapidly. Studies indicate that spacecraft currently in Mars orbit could potentially conduct flyby observations with relatively modest propulsion requirements during July through September 2025. The European Space Agency's Mars Express, NASA's MAVEN, or India's Mars Orbiter mission could theoretically be repurposed for this historic encounter. Earth-based missions face much more challenging requirements. Any post-discovery launch would require delta V values exceeding 24 kilometers per second, far beyond the capabilities of most launch systems. The narrow observational window before perihelion makes 3I divided by Atlas a time-critical target for in situ exploration. This might be our only chance to directly sample material from the Milky Way's ancient thick disk. No human-made object has ever traveled to another star system. But here we have a piece of another star system that has come to us, carrying samples from an era of cosmic history we can access no other way. The missed opportunity weighs heavily on planetary scientists. Dr. Andrea Martinez, who studies interstellar objects at the Jet Propulsion Laboratory, described it as like having a library from ancient Alexandria materialize in your backyard for a few months before vanishing forever. But even without spacecraft visits, the ground-based observations of 3I divided by Atlas are revealing profound insights about the processes that shaped our galaxy billions of years ago. Yet when scientists calculated the odds of what we're witnessing, they discovered something that would shake their understanding of cosmic probability to its core: the astrobiology connection. The astrobiology implications are particularly intriguing. The detection of complex organics and unusual isotopic ratios in 3I divided by Atlas carries profound implications for understanding the distribution of life-building materials throughout the galaxy. The comet's ancient age means it carries chemical signatures from stellar populations that formed when the universe was younger and had different metallicity patterns. The organic inventory of 3I divided by Atlas could reveal whether life's building blocks are universal features of planetary formation or depend on specific stellar and galactic environments. The unusual carbon chemistry suggests formation conditions unlike anything we see in modern planetary systems, possibly indicating that the early universe was more conducive to certain types of prebiotic chemistry. Analysis of the isotopic ratios could reveal information about the stellar nucleosynthesis processes that were dominant during cosmic noon, the peak epoch of star formation 10 to 11 billion years ago. Different generations of stars produce different isotopic signatures, and 3I divided by Atlas might be carrying samples from stellar populations that no longer exist in the same form. Dr. Robert Kim, an astrobiologist studying interstellar organic chemistry, explains it this way. 3I divided by Atlas is like receiving a message in a bottle that's been floating in the cosmic ocean for 10 billion years. The message isn't words, it's molecules, chemical signatures that tell the story of what the galaxy was like when it was young. The potential for 3I divided by Atlas to harbor preserved materials from the peak epoch of star formation makes it an invaluable archive of conditions that may have been conducive to early life elsewhere in the galaxy. If life arose during that era in other star systems, objects like 3I divided by Atlas might be carrying preserved samples of those ancient biochemistries. This connects to one of the deepest questions in astrobiology. Is life a universal feature of cosmic evolution, or does it depend on specific, rare conditions that might not exist everywhere? The chemistry of 3I divided by Atlas provides clues about the chemical diversity that was possible in the early universe, which in turn tells us something about the likelihood that life could have emerged in different environments. If confirmed, the detection of complex organic compounds would make 3I divided by Atlas one of the most organically complex objects ever studied in detail. The preservation of complex organics over billions of years of interstellar travel would demonstrate that such molecules can survive the harsh environment of space far longer than previously thought. The implications for astrobiology would be profound. If complex organic molecules can survive interstellar journeys, then the building blocks of life might be much more widely distributed throughout the galaxy than we realized. Comets like 3I divided by Atlas could be carrying prebiotic chemistry between star systems, seeding planets with the molecular ingredients needed for life to emerge. This connects to the concept of panspermia, the idea that life or its precursors might spread throughout the galaxy via comets, asteroids, or other interstellar objects. While the idea remains highly speculative, the discovery of preserved organics in 3I divided by Atlas lends some credibility to the possibility that biological materials could survive interstellar transport. But the organic chemistry findings also raise new questions about the formation and evolution of 3I divided by Atlas. How did complex molecules survive the violent ejection from the parent system? How were they preserved during billions of years of cosmic ray bombardment? What does their current distribution tell us about the internal structure and evolution of the comet nucleus? These questions are driving new research into the physics and chemistry of long-term space weathering. Laboratory experiments are being designed to simulate the effects of cosmic ray bombardment on organic compounds over geological timescales. Computer models are being developed to understand how complex molecules might be protected within comet nuclei during interstellar travel. But there's something even more remarkable about 3I divided by Atlas that goes beyond its chemical composition or its ancient origins. Something that challenges our understanding of probability itself. But here's the most remarkable thing about 3I divided by Atlas: the detail that transforms this from an interesting scientific discovery into something that should fundamentally change how we think about our place in the cosmos. Remember those unusual orbital characteristics that led some scientists to speculate about artificial origins? The alignment with the ecliptic plane, the close approaches to multiple planets, the timing of perihelion on the far side of the Sun from Earth. While the scientific consensus firmly supports a natural explanation, these characteristics reveal something equally extraordinary. 3I divided by Atlas isn't just any random visitor from interstellar space. Its trajectory suggests it originated from a specific region of the thick disk, a stellar population that includes some of the oldest planetary systems in our galaxy. The orbital analysis indicates it was ejected during the early stages of planetary formation around a star that was already ancient when our sun was born. This means 3I divided by Atlas is quite possibly a fragment from one of the first generations of planetary systems in our galaxy. It might contain materials that represent our earliest attempt at creating worlds, the cosmic prototype for the processes that would eventually create Earth and the other planets in our solar system. The chemical signatures we've detected, the unusual isotope ratios, the complex organic molecules, all of these might be samples from the galaxy's first experiments with planetary formation. We're not just studying a comet. We're examining a fossil from the dawn of planetary science on a galactic scale. And it came to us. Out of all the possible trajectories through the galaxy, out of all the star systems it could have visited, out of all the moments in cosmic time when it could have passed through, 3I divided by Atlas arrived at our solar system at exactly the moment when we had developed the technology to recognize it, study it, and understand what it represents. The statistical probability of this happening is almost impossibly small. The galaxy is vast, containing over 100 billion stars. The timescales involved are enormous, spanning billions of years. The window during which we've had the capability to detect and study interstellar objects is a tiny fraction of cosmic time, measured in decades rather than eons. Yet, here we are, a young species on a young planet orbiting a middle-aged star, receiving a visit from an object that carries within it the history of our galaxy's youth. It's as if the universe has delivered to us a message that we're only just now capable of reading, a letter from the deep past that arrived at precisely the moment we learned the language needed to understand it. This convergence of cosmic history and human capability represents one of those rare moments when the vast scales of space and time align to create an opportunity for understanding that may never come again. We are living through a unique intersection of cosmic evolution and technological development that has opened a window into the deep history of our galaxy. But perhaps the most profound realization is this. If the timing is this perfect, if this ancient messenger arrived at exactly the right moment for us to study it, what does that say about our place in the cosmic story? Are we witnessing an impossible coincidence? Or are we part of something larger that we're only beginning to understand? 3I divided by Atlas represents far more than a single interstellar visitor. It is the harbinger of a new era in our understanding of galactic evolution, planetary formation, and the cosmic distribution of the materials that make life possible. Its extreme age connects us to an epoch of cosmic history we've never been able to study directly. Its unusual chemistry reveals processes that occurred in stellar environments unlike anything in our local cosmic neighborhood. Its preserved organic molecules suggest that the building blocks of life might be far more widely distributed throughout the galaxy than we ever imagined. The storm of objects gathering around 3I divided by Atlas includes not just the physical debris in its coma, but the constellation of new questions, discoveries, and revelations it has brought to our understanding of the universe. Every unusual property, every unexpected measurement, every deviation from our models has opened new avenues of research and forced us to reconsider our assumptions about how the cosmos works. The carbon dioxide chemistry that challenged our understanding of volatile behavior in ancient protoplanetary disks. The magnetic properties that revealed new types of interactions between small bodies and the solar wind. The polarimetric signatures that showed surface compositions can be far more diverse than we realized. The rotational characteristics that demonstrated how long-term evolution can modify objects in ways we didn't anticipate. The isotopic ratios that provided insights into stellar nucleosynthesis processes from the early galaxy. The organic inventory that suggested new possibilities for the distribution of prebiotic chemistry throughout the cosmos. The trajectory analysis that connected us to the thick disk stellar population and the violent early epochs of galactic evolution. The timing that brought this ancient messenger to us at precisely the moment we could recognize its significance and decode its message. As this ancient wanderer continues its billion-year journey through space, it carries with it the accumulated wisdom of cosmic time. It is a library of stellar nucleosynthesis, a museum of planetary formation processes, an archive of interstellar chemistry from an era when our solar system was merely scattered dust in a molecular cloud. But perhaps most importantly, 3I divided by Atlas has shown us that we are not alone in the galaxy in the way we might have thought. We are surrounded by wandering messengers from other worlds, other times, other stellar environments. The space between the stars is not empty. It is filled with the debris of countless planetary systems, each object carrying its own unique story of cosmic evolution. The universe is far stranger, far more connected, and far more active than we realized. Objects like 3I divided by Atlas are constantly crossing the boundaries between stellar systems, mixing materials, sharing chemical information, creating a galactic ecosystem that operates on timescales we're only beginning to appreciate. We are part of that ecosystem. The elements in our bodies, the chemistry that makes life possible, the processes that formed our planet, all of these connect us to the broader galactic community that 3I divided by Atlas represents. We are not isolated observers of cosmic phenomena. We are participants in an ongoing story of cosmic evolution that connects every star, every planet, every wandering object in the galaxy. 3I divided by Atlas has given us our first detailed glimpse of that larger story. It has shown us that the galaxy is filled with ancient wanderers carrying messages from the deep past, and that sometimes, if we're very lucky and very prepared, one of those messengers will come close enough for us to read what it has to say. The storm of objects gathering around 3I divided by Atlas is ultimately a storm of understanding. Each new observation, each refined measurement, each deeper analysis adds another piece to our growing comprehension of our place in the cosmic story. We are living through a unique moment in the history of human knowledge, a time when we're learning to read the messages that the universe has been sending us all along. The magnetic anomalies that revealed complex electromagnetic interactions we never knew were possible. The chemical impossibilities that forced us to expand our models of how matter behaves in extreme environments. The size paradox that showed us how activity and evolution can mask the true nature of ancient objects. The rotational mysteries that demonstrated how billions of years of travel through space can alter the fundamental properties of matter itself. The polarimetric signatures that opened our eyes to surface compositions unlike anything in our solar system. The organic detections that suggested life's building blocks might be wandering between the stars. Each discovery has been like opening a door to a room we never knew existed, only to find that room contains doorways to even more mysterious chambers. 3I divided by Atlas has shown us that our understanding of the universe is far more limited than we thought, but also far more expandable than we dared to hope. As 3I divided by Atlas disappears back into the darkness of interstellar space, it leaves behind more than just scientific data and research papers. It leaves behind a transformed perspective on our cosmic environment and our place within it. We now know that we live in a galaxy filled with ancient wanderers, that the space between stars is alive with the debris of countless worlds, and that sometimes the universe delivers to us exactly the information we need to understand ourselves and our place in the grand story of cosmic evolution. The future will bring more visitors like 3I divided by Atlas, each one carrying its own unique message from the depths of space and time. The Vera Rubin Observatory will soon begin its systematic survey, turning the discovery of interstellar objects from rare events into regular occurrences. We will learn to read an entire library of cosmic messages, each one adding to our understanding of how the galaxy works and how we fit into its grand design. But none of those future discoveries will quite match the impact of 3I divided by Atlas, the ancient messenger that arrived at exactly the right moment to show us that we are part of something much larger and more wonderful than we ever imagined. This 7 billion-year-old time capsule has given us our first taste of what it means to be citizens of the galaxy, connected by invisible threads of matter and energy and history to every corner of the Milky Way. The next time you look up at the night sky, remember 3I divided by Atlas. Remember that out there in the darkness, ancient messengers are traveling between the stars, carrying with them the history of worlds we will never see and the chemical fingerprints of cosmic processes we've never directly witnessed. Remember that we are made of the same materials, shaped by the same processes, participants in the same ongoing adventure of cosmic evolution that has been unfolding for billions of years and will continue long after we are gone. And remember that sometimes, if we're very fortunate, the universe sends us exactly the message we need to understand our place in its grand and ancient story. Hit subscribe to journey deeper into the cosmic mysteries that surround us every night.